We assume they are smart, but a computer has an IQ of exactly 0. It possesses no independent thought, intuition, or mind of its own. Beneath the sleek interfaces, a computer is strictly a programmable electronic state machine. It is a rigid executor of rules, processing the raw data we feed it according to the specific instructions we provide. Strip away the desktop, the applications, and the text. At the lowest physical level, the machine does not understand human language. It only recognizes one physical reality: the presence or the absence of electrical voltage in a circuit. This is the foundation of discrete binary logic. A switch is either closed, allowing current to flow, represented as a 1, or it is open, stopping the current, represented as a 0. Every digital action, every video rendered, and every message sent is simply the high-speed routing of these zeros and ones. To actually understand how a computer works, we have to stop looking at the screen. We need to trace the physical pipeline that translates human intent into mechanical execution. Computation began entirely in the physical realm. To track data, early humans manipulated discrete units. Moving a wooden bead along a rigid track on an abacus was the first time we outsourced mathematical memory to a physical object. By the 17th century, human hands were replaced by automated physics. Inside calculating devices like the Pascaline, interlocking brass gears forced numbers to carry over automatically. The math was baked directly into the metal. The leap to programmable computing required a machine that could change its function based on instructions. The analytical engine used a dense matrix of columns, where the physical arrangement of the hardware dictated the exact sequence of mathematical operations. Physical gears are slow and prone to mechanical wear. The solution was thermionic emission. By using glass vacuum tubes, engineers could route electrical signals across metallic filaments without moving parts, controlling data at the speed of light. That architecture was eventually miniaturized. Fragile vacuum tubes were replaced by solid-state transistors, allowing thousands of logic gates to be packed into a single integrated circuit encased in silicon and plastic. Whether the substrate relies on brass gears or microscopic silicon, the task of the hardware remains identical. It routes inputs through a deterministic physical architecture to yield a specific output. A fully assembled motherboard is inert on its own. It is a collection of pathways with no traffic. To execute a task, the hardware requires logical instructions, the software. The foundational instruction set is the operating system. It is the initial spark that wakes the system up, managing the hardware resources and providing the environment where all other applications operate. But there is a massive translation barrier here. The hardware only understands voltage levels. When you type a sentence or click a mouse, those high-level human inputs are completely foreign to the physical circuitry. This requires a translator. A compiler takes our human-readable syntax and shatters it into raw machine language. It converts text and commands into the cascading, uniform streams of binary zeros and ones that the circuits can actually process. Every computing task you perform relies on this invisible, continuous translation layer. It bridges the gap between your conceptual thought and the physical electronics doing the work. Before those binary instructions can be executed, they have to be stored. The system manages this by splitting memory into two primary domains: an active staging area and a permanent vault. The staging area is random access memory, or RAM. This is a high-speed, temporary environment. It holds the data and applications that the computer is actively working on right now. When you initiate a file download or load a complex application, the data isn't fully formed yet. It is actively being built, percentage by percentage, and held within this RAM sector while the process completes. But this speed comes with a physical vulnerability. RAM is volatile. It relies on a continuous supply of electrical power to maintain the data states of its transistors. If you cut the power, those electrical states collapse. Any uncommitted data, like a partially downloaded file or an unsaved document, vanishes instantly. The staging area is wiped clean. This is why the system requires a permanent vault, read-only memory, and secondary storage drives. These components are non-volatile. They lock data into permanent physical states that survive without constant electricity, safeguarding finished files and the operating system. Computation is an ongoing balancing act between these two domains. The system leverages the rapid, volatile speed of RAM to build data, and then commits it to the secure permanence of storage. Once data is staged in RAM, it requires an engine to process it. That engine is the central processing unit. It is a strict, deterministic executor of the binary code. Inside the CPU, the workload is divided into 3 precise stages. First, the data packet arrives from RAM into the local buffer, known as the memory unit. Next, the control unit acts as the internal traffic director. It reads the incoming instruction, determines exactly what mathematical or logical operation is required, and routes the data to the correct location. The destination is the arithmetic logic unit. This is the core execution chamber. Here, the logic gates physically transform the zeros and ones, executing the mathematical calculations required by the software. With the calculation complete, the processed data routes back out through the memory unit, ready to be sent to an output device or stored permanently. Every digital action you experience is just this loop repeating. Whether it's registering a single keystroke or rendering a complex 3D environment, it is simply billions of these memory, control, and logic cycles executing every single second. This CPU pipeline is incredibly fast, but it is entirely isolated. It exists in a closed loop, restricted to interpreting discrete, fixed binary values. Look at this split chart. On the left, we see a smooth, curving sine wave representing physical reality, things like a human pulse, a shift in temperature, or the velocity of a car. These are analog signals, defined by continuous, constantly shifting data. On the right, we see the rigid stair-step square wave of digital logic. Traditional analog devices, like a mercury thermometer or a mechanical speedometer, measure this physical continuity directly. They provide immediate feedback, but they lack the capacity to store that data long-term or run complex logical operations on it. The physical universe operates in analog continuity. But to harness analytical computing power, that continuity must be forced into the strict, discrete boundaries of digital logic. To bridge this gap, engineers developed hybrid architectures. These systems combine physical analog sensor measurement with digital processing power. Modern consumer technology, from smartphones to smartwatches, operates on this hybrid architecture. These devices absorb analog inputs, the pressure of a finger, the sound waves of a voice, or a fluctuating heart rate. It translates this through an analog to digital converter. This component samples the continuous physical input and chops it into a sequence of discrete binary blocks. It forces the chaotic wave into structured ones and zeros. Once digitized, that real-world data feeds directly into the volatile RAM. From there, it is pulled into the CPU, routed by the control unit, and calculated by the arithmetic logic unit. Computing is ultimately a translation engine. It captures the continuous physics of reality, discretizes it into binary logic, processes it deterministically, and outputs actionable order.